Hey guys, Boer Commander here, and welcome to the second video in the series of operations research. Now, in the first video I introduced to you some of the basic concepts and how to start off the Simplex method. Now in this video I'll be further working on the Simplex method, finalizing that, introducing some of the concepts needed to truly finalize your understanding of the Simplex method, and then I'll be introducing you to the Big M method of solving problems when we are encountering artificial variables. Now, in the last video I introduced to you the form of maximizing some function. Maximizing, say, x1 plus x2. Now, we usually encounter problems in the maximization form, but there are also other forms. We might be asked to minimize x1 plus x2. Now, don't be alarmed when you encounter this, because if I told you to maximize some function x1 plus x2, I'm asking you to get the biggest value of the sum of x1 and x2. So if I ask you to minimize this, that is equivalent to maximizing. If I ask you to minimize z, that is the equivalent of maximizing negative z. So we simply multiply by minus 1. And this is fairly intuitive, because if I ask you to find the smallest value of the sum of two numbers, that's simply going to be the biggest value of the sum of the negative values of those two numbers. So that's just how we transform the forms of the Simplex method if we encounter a minimization. So we transform it to a maximization, maximize negative z, and then we simply plug this into the Simplex method. So that is covered that. Now I'm going to move on to a very important concept, something that I did not mention in the previous video because there was not sufficient time. And in this video I'll show you what happens if we have constraints imposed on the decision variables themselves. If you perhaps have read through some textbooks or you've seen this in your classes, you'll often see that your variables, your decision variables, will be of the form greater than or equal to 0. Now what this means is that your value of x1, your decision variable, it has to be greater than or equal to 0. Well, what happens if I have a different form? Say I have x1 must be greater than or equal to 10. Well, what we do here simply is we move the 10 to this side, we subtract it. So we say x1 minus 10 is going to be greater than or equal to 0. And then we use a substitution. So we let x1 prime be equal to x1 minus 10. And that means that x1 prime now is going to be greater than or equal to 0. So that's how we carry out this simplest form of the transformation. You'll often see it in an example if it will be state x1 is greater than or equal to 10. And then all you simply do is you bring the 10 over to the left hand side, and then you use a substitution. You can call it anything you want, but I like to call it x1 prime. And you set that equal to x1 minus 10, and then you can have your model in the form of x1 prime being greater than or equal to 0. Now another concept that is very important is an unrestricted in sign variable. Unrestricted in sign. Well, what that means is our variable, we can call it x2 in this scenario, x2 is unrestricted. It can be positive, it can be 0, or it can be negative. It's unrestricted. Its sign does not matter. It can be positive, 0, or negative. Well, what we do in this case is, say we have x2 being unrestricted, and we want to transform it into a nice form so that it has to be greater than or some value has to be greater than or equal to 0. Well, what we do in this case, we say that x2 prime minus x2 prime prime has to be greater than or equal to 0. and I'll show it in an illustrative example to you. But what happens is that this x2 prime subtracted from this x2 prime prime is set equal to what x2 is. Well, from here on we know that x2 prime will be greater than or equal to 0, or x2 prime prime will be greater than or equal to 0. And then we have made our model into a nice form that can be used in the simplex method, and that's one of the things that is very important when you are answering any method, any question on the simplex method, is you state your variables. Say I'm maximizing x1 plus x2. We state our constraints subject to x1 is less than or equal to 5, and say x2 is less than or equal to 6, and then we must also state the bounds that are placed. So the bounds on x1 and x2, and usually the most common ones that you'll see is just simply x1 and x2 are greater than or equal to 0. You have to always include the bounds on x1 and x2, otherwise you will lose marks in a question or in an assignment or in the test when you encounter this. Always remember your bounds. So I will bring all these ideas introduced to you now together in an example where I show to you how do we transform a model. Okay. So say we are asked to find the minimum value of x1 plus x2 subject to the absolute value of x1 being less than or equal to 3 and x2 being equal to -1. So these are our constraints. And say further that you're given the bounds on x1 and x2 are that they are both unrestricted. So we might think that if we want to start, if we ignore this information, then we will get the incorrect answer in our question. So what we'll have to do is we'll have to transform both x1 and x2. So firstly, let's go and look at our constraints. The absolute value of x1 being less than or equal to 3 means that x1 must be less than or equal to 3, and x1 must also be greater than or equal to -3. And x2 is simply equal to -1. So how would we transform these two variables, x1 and x2, given that we know that they are unrestricted? Well, we're going to simply say that x1 prime minus x1 prime prime is set equal to x1, and x2 prime minus x2 prime prime is set equal to x2. Then we transform our equation to x1 prime minus x1 prime prime has to be less than or equal to 3, x1 prime minus x1 prime prime has to be greater than or equal to -3, and then lastly we have x2 prime minus x2 prime prime is now equal to -1. So we've transformed our constraints into a form that we can go and use the simplex method on. So here it's simple. We would add a slack variable. You add slacks. Here we'll have to transform it using both excess variables and artificial. And here we would simply have to add an artificial variable. And I'll introduce these concepts and why they are needed in a few moments. So, just to reiterate, this minimization form is another form of what we'll see of a linear programming problem. And a minimization is always equivalent to maximizing the negative of x1 plus x2, which we'll simply go and use in our row 0 of our Simplex Tableau. I've introduced to you the ideas that our constraints might be, or the bounds on the decision variables themselves might be different from simply being greater than or equal to 0. They might be of a form such that they are unrestricted, and in which case we simply introduce that variable which is unrestricted prime subtracted from that variable to double prime must be greater than or equal to 0. And alternative forms simply involve a very simple substitution. In the case of x1 being greater than or equal to 10, we simply subtract the 10 on both sides, so we're left with x1 minus 10 is greater than or equal to 0, and then we transform it by saying that x1 prime is greater than or equal to 0. So this is how we would do some simple transformations if we are given that the bounds of our variables themselves are different from being greater than or equal to 0.